Hello, everyone. Thanks for joining. We're going to get started here very soon. Before we do, going to get everyone just about a minute to join in. Welcome, everybody, to the Climate Scale Solutions with Nuclear Produced Hydrogen Net Zero Carbon Synthetic Fuels webinar. Really appreciate you all joining today. My name is Dylan Adler. I'm facilitating on behalf of the Nice Future Initiative. Very briefly, I'm going to go over a quick few logistical items for this webinar. Okay, so all attendees are in listen-only mode, meaning you won't be able to access your audio or video. We will be recording today's webinar, and closed captioning is enabled. You can choose to turn on your subtitles if you wish. You go to closed caption and click show subtitle. It'll be one of the options listed on your Zoom screen. If you have any technical issues, please click the raise hand function and I will message you directly via chat. Otherwise, the chat will only be available for panelists to use to communicate. And for any audience questions that you may have for the speaker, please click the Q&A button. It'll open, it looks like those two chat bubbles. It'll open a dialog box. You'll be able to post a question in there. Only you'll be able to see your question until it is answered by a panelist, and then everyone will see it. But ideally, questions will be answered during the Q&A function that we're going to have after each speaker is completed giving their presentation. Lastly, this webinar, as I said, is being recorded and it's going to be available afterwards on the Nice Future website for replay. And now I will pass it over to our moderator, Eric. Eric, welcome. Thank you.
Thanks, Dylan. Welcome, everybody. We're excited to have you all here for this webinar. And we'll be introducing the speakers as we go. But first, Jason Marcinkowski is going to give you a little orientation to some of the Nice Future activities.
Welcome. My name is Jason Marcinkowski, and I'm the Program Manager for Integrated Energy Systems and Flexible Plant Generation and Operation in DOE's Office of Nuclear Energy. I'm here today on behalf of the Nuclear Innovation Clean Energy Future, or NICE Future Initiative. NICE Future is the sole nuclear-focused initiative of the Clean Energy Ministerial, which will hold its 13th annual meeting of ministers and the clean energy community, hosted by U.S. Secretary of Energy Jennifer Granholm from September 21st through 23rd, 2022 in Pittsburgh. NICE Future is led by the U.S., Canada, Japan, and the U.K., with 9 other participant countries and 18 partner organizations to explore the potential of nuclear innovations to accelerate progress toward climate and clean energy goals. One area which is gaining global momentum and interest is hydrogen, and particularly the topic of today, synthetic fuels. Synthetic fuels can be made from clean hydrogen produced from nuclear energy and a source of carbon, which can be CO2. From my own vantage point in the U.S. Department of Energy, we're focused on near-term technology to use hydrogen produced from nuclear reactors for the production of drop-in synthetic fuels suitable for transportation. This is one way we can get clean, reliable nuclear energy into the transportation sector. Drop-in means they can leverage the massive, fully developed fuel distribution infrastructure and existing vehicle fleet. And there's technically viable technologies today with room to advance. This will provide us with clean fuel with no additional emissions, mitigating the emissions otherwise produced by traditional fuel production and use. They provide us practical energy for use in transportation and off-road vehicles and machinery. Because of their inherent properties, they're high in energy density, they're dispensable liquids with high activation energy, making them relatively safe. They provide us with energy security. These fuels can play a critical role in our economy and national security for fundamental needs like mining, construction, agriculture, aviation, defense, and long-distance transport of goods. These roles are hard to decarbonize because of the power density and energy density required on board the vehicles and their refueling rates. For several of these vehicles, they can't readily access the public fueling infrastructure and need energy that's transported and transferred to the vehicle at the site of use. So I'm really excited to get to know about all of your work in this technology area to help us reduce emissions in the near term and make progress toward a clean energy economy. Now, Jose Bermudez will speak on behalf of the Hydrogen Initiative.
Thank you very much, Jason, and good morning for you in the US. Good afternoon here from Paris. My name is Jose Bermudez. I'm working as an energy technology analyst at the International Energy Agency, and part of my role is being coordinating the Clean Energy Ministerial Hydrogen Initiative, which is what I'm going to introduce in the next few minutes. The Clean Hydrogen Initiative is an initiative that is framed within the framework of the Clean Energy Ministerial, and that was launched in 2019 in Vancouver, with the objective of rising ambition to advance commercial scale low carbon hydrogen deployment in the long term globally and across all the sectors of the energy sector. The reason why this initiative was launched is because well, the adoption of hydrogen, or in this case low carbon hydrogen, needs for long-term plans, for aligning visions and goals to make sure that we are following the same direction to ensure that hydrogen uptake can occur, and that this can be planned effectively and defining the correct policies for this to happen. The ambition of creating these platforms was to create this partnership, to work together and facilitating the achievement of those global goals that were defined on the Hydrogen Energy Ministerial in Japan in 2018, and also to facilitate this adoption, the large-scale adoption of clean hydrogen fuel cells across all regions, national governments, and municipalities. The initiative right now has around 25 governments that are involved at different levels, but is particularly intrinsic the engagement are our 5 colleagues, which are the United States, Canada, the European Commission, Japan, and the Netherlands. In addition, as members of the initiative, or as partners of the initiative, we have the Hydrogen Council, which is the largest initiative from the private sector in the world, and that has hundreds of members, and a series of individual companies that work on the development of electrolyzers, on the energy system, on the energy generation, and also on some end users for hydrogen. In addition, we have more than 50 ports, ports association, and port authorities that are involved in one of the activities that I will describe very quickly now. And finally, we also have several activities in coordination with other international hydrogen initiatives, such as the International Partnership for Hydrogen and Fuel Cells in the Economy, the Hydrogen Council, of course, the Hydrogen Technology Collaboration Program of the IEA, Mission Innovation, IRENA, World Energy Forum, and many others. Right now, we have a series of activities already ongoing. The first one is the working group on global aspirational goals, which is led by the European Commission. And there is an effort to track existing government goals and how they develop and which kind of policies are adopted to reach them all across the world with the idea of tracking progress on this area. Then we have the Global Ports Hydrogen Coalition, which is another initiative focused specifically on the role of ports and port authorities in the development of hydrogen technologies, in the adoption of these technologies and scaling up production and consumption of hydrogen, and also on how hydrogen-derived fuels can contribute on the decarbonization of port activities. We have the Hydrogen Twin City program that was launched at the end of last year in COP, and that is aiming to announce the first cities participating in the next few months. And it's a competitive collaboration between cities around the world, trying to pair them to put in contact cities that are more advanced on the planning and the development of the idea of hydrogen can play in the city, and municipalities or regions is not only dedicated for cities. So pairing those cities that are more advanced with other cities that are at more early stages of thinking, trying to share best practices, knowledge, contributing to staff exchanges with the idea of facilitating knowledge sharing. We have also a working group on international hydrogen trade and supply chains, which is a collaboration effort of a series of policymakers of the different members of the initiative, trying to address those barriers that are today preventing the development of an international hydrogen market, and trying to find policies, share practices, and share goals with the objective of kicking off this international hydrogen trade. And finally, we have a regional working group on Northwestern Europe, in which a total of up to 10 countries right now are working together in establishing a regional hydrogen market, with the idea that this model can be replicated in other regions of the world and can be the first hubs of this larger and future international hydrogen market. And finally, particularly the role of the IEA, a part of being the coordinator of this initiative, is to publish annually a global hydrogen review, which we are now in preparation, and is going to be released in September in the next Clean Energy Ministerial meeting, with the objective of tracking policies and progress in hydrogen markets, development of infrastructure, the adoption of new supporting schemes, and also providing analytical insights of certain specific topics of interest, which you can guess in the situation of this year is actually energy security. And that's all from my side. Thank you very much for the invitation, for having the opportunity to present the initiative today. And back to you, Eric.
Thank you, Jose. And thank you, Jason. Also, thanks to the Energetics staff for hosting the webinar, and to Julia Visconti and John-Michel Murray of the Nice Future team for their hard work to organize this event. Today, we have over 70 people here participating, and we have registrants from around the world, which is what we had hoped to do. Please join us for other webinars in this series on other cutting edge topics, and you can also sign up for announcements on the nicefuture.org website. This webinar is one of the activities in preparation for the 13th Clean Energy Ministerial, which will be held during the first ever Global Clean Energy Action Forum, a joint convening of the CEM 13 and the 7th Mission Innovation Ministerial. And that will be held in Pittsburgh in the United States from September 21 through 23 this year. The Global Clean Energy Action Forum will be hosted by the U.S. DOE Secretary Granholm. And it will be a great opportunity to put nuclear energy's innovations back at the center of the clean energy plans and actions. This webinar is focused on zero carbon synthetic fuels. Clean hydrogen production is being pursued in many countries due to its versatility as a clean energy carrier. And the combination of nuclear energy and hydrogen offers significant promise as a climate change solution. In the United States, nuclear energy operating on the grid today provides about 20% of our nation's electricity and about half of our non-emitting electricity. This fleet of 94 nuclear reactors is a workhorse for clean, safe, reliable, and firm generation capacity. Over the last 25 years of operation, these reactors have reduced carbon emissions in the US by 16 billion metric tons. But today, that fleet only provides electricity to the grid. In the US and in many of the countries represented on the panel today, we've been rethinking how we can use our current clean energy generators to do more than just put electrons on the grid. We are working to design and deploy new systems that will allow continued provision of electricity, but will also provide heat and steam to support other energy demands, thereby providing an avenue for decarbonization of industry and transportation in addition to the electric grid. Today's discussion will provide some exciting insights about these developments. One thing I'd also like to point out is that there's a kind of, the way that hydrogen is discussed in the energy transition more broadly, it's often thought of as something that's precious, probably expensive, and that is really kind of a zero-sum game with electricity. Like if you are making electricity, you're probably, I mean, if you're making hydrogen, then you're taking away from clean electricity production somewhere else. And I think one of the things that we should really keep in mind is that with nuclear energy, because of its power density, because we can build a lot of nuclear in kind of a small area, we don't have a lot of the constraints about quality of solar resource or quality of wind resource or proximity to transmission. A lot of these kinds of issues are maybe we don't have those issues with nuclear energy. And optimized nuclear generation for making hydrogen has the potential to make very large amounts of hydrogen. So we may not be in this kind of zero-sum game with clean electricity. And I think that's really something that is unique about what nuclear has to offer in the hydrogen space. We hope today's discussion will provide policymakers with important insights from worldwide experience. And we've asked each speaker to give a presentation of about 10 minutes. And following each presentation, there'll be a Q&A session. So I'll come back on and ask questions for the speaker. Please, if you have questions, use the Q&A function and I will be able to engage the speakers with your question. So next we have Elena Teplinsky and Carlos Lipner. Elena is a partner and the deputy leader of the energy industry team and a member of the nuclear and hydrogen practices at Pillsbury Law. She's also the co-leader with Carlos of the Nuclear Hydrogen Initiative. Carlos is the director of Global Nuclear Energy Strategy at the Clean Air Task Force, an environmental non-governmental organization focusing on global decarbonization. And at CATF, Carlos leads the nuclear program and its initiatives to broaden and scale up the application of nuclear energy around the world. Their presentation will cover the role that nuclear energy can play in catalyzing the hydrogen economy, and it will also discuss the work of the Nuclear Hydrogen Initiative to advance that role. Welcome, guys. Good to see you.
Thank you, Eric, very much. Thank you, Jason, and everyone. It's a delight to be part of this conversation here, and to talk a little bit about the work and the that we have been doing with the Nuclear Hydrogen Initiative. And as a way of setting the context, the NHI has been active for the last year or so, and but we will be formally launching the initiative for media purposes within the next 2 to 4 weeks. And so for those members of the press that might be present here, please treat the presentation here as off the record. And if there's a desire to publish the information, please don't hesitate to contact me or Alina for this as well. But to put in context, about 2 years ago, Clean Air Task Force convened a 2-day workshop focused on the nuclear solution to produce clean hydrogen, and the purpose of that was really to explore this exchange of information and really be intentional about not only focusing on the nuclear industry, but bringing folks from different parts of the hydrogen ecosystem and discuss this potential solution. And out of that work, it blossomed and it grew into what we now call the Nuclear Hydrogen Initiative, with the purpose and objectives, as you can see here, to raise awareness to the role that nuclear technologies and nuclear energy can play in creating a very large-scale zero carbon hydrogen market. But addressing policies, addressing technology and licensing issues, talking about markets and business models, as well as access to financing. So with that, we focus on different themes, and those themes evolved into different working groups. Next slide, please, in which there has been very active engagement. So I'll briefly discuss these, and then my colleague Alina will talk a little bit more about specifically on policies and opportunities. But from the policy working group, it's been a fantastic engagement here, where we, of course, discuss and elaborate potential policy recommendations, advocacy initiatives, and 2 key deliverables of this working group within the last year have been first, in the United States, the Department of Energy issued a request for information earlier this year on hydrogen, on a variety of subjects, including hubs, which we'll be talking about shortly. But so NHI provided a response representing the voices of the participants. And so this has been a very collaborative effort. And then we have worked together to prepare and develop a white paper, which I'll talk shortly about, a compilation of all the various hydrogen roadmaps and strategies that have been issued around the world. So this working group has been very, very active. Secondly, this focus on technology, R&D, in licensing, all the different challenges and perhaps opportunities too, related to how to apply nuclear energy to produce clean hydrogen and ammonia. So there have been a lot of discussions and learning from each other in this working group. Next slide, please. The next 2 are one focus on markets and commercial partnerships, and we have learned so much here from different projects that are ongoing around the world, not only in the United States, but in Canada, in Brazil, in France, in the UK, in many other parts, and from these projects that are leading towards demonstrations of potentially nuclear produced hydrogen. Have been tremendous to learn not only about the opportunities and how these are being structured, and whether they're related to high temperature electrolysis, low temperature electrolysis, different types of ways to produce clean hydrogen via nuclear technology. So this has been a very engaging working group. And then finally, the finance working group, and as we understand, there will be new business models, perhaps not required, but will be understood to deploy these opportunities, these solutions. And we see already a change in the marketplace overall, how this is progressing. So having access to financing and how to structure these projects have been quite an interesting discussion in this working group as well. So very dynamic last year or so in these 4 key areas related here. Next slide, please. As I mentioned on the outset, the intention here was to broaden the discussion within the nuclear industry. I think for quite a while, we tended to talk amongst ourselves, but the goal here was really to expand and bring stakeholders from across the hydrogen economy ecosystem and learn from each other and look at different perspectives. So here's just a glimpse of those that have been actively participating, and it continues to grow. Just last week, we've had interest from South Korea to an organization there to join us. So we continue to expand. And maybe I didn't mention, but there's no cost to join. This is really a forum to share information and learn from each other and discuss and collectively collaborate to progress the solution of nuclear hydrogen. Next slide, please. So I mentioned that we'll be formally launching the initiative in the next 2 to 4 weeks. So the website is listed here. You can start perusing the information there, good references, and it points to different areas that are relevant for the nuclear hydrogen sphere. And I mentioned our one of the first deliverables that we've had is this white paper related to the different global policies for different jurisdictions that are in place for hydrogen across the world. As you know, the last 2 years have been very dynamic period, with many countries issuing their roadmaps and their policies, some of them including nuclear. So we do acknowledge that here. And we're also recommend some initiatives and some policies for consideration at a high level that might be of interest to all of you as well. So to continue the discussion, I'll pass it to my colleague Elena to talk about policies. Elena. I think you're on mute, Elena, sorry.
Thank you so much, Carlos, much appreciated. Can you guys see my camera?
Yes.
Okay, great. So Carlos has provided a really good overview of the initiative, and maybe I'd just like to summarize what we've learned from the initiative, I think in 3 points, 3 key points. The first point is that nuclear can provide electricity and heat on the 24/7 basis, so we don't have any intermittency issues. The second point is that it's not just electricity, but also heat, which gives nuclear energy a unique advantage and potentially being paired quite well with the high temperature electrolysis process, which could really bring down costs and create efficient hydrogen production. And the third point, which Eric also mentioned, is just the density of nuclear, and as an energy source, which really reduces the geographic constraints for nuclear hydrogen production. So with those 3 points in mind, it seems very clear that nuclear energy can be not just a source for hydrogen production, but in fact, it can be a catalyst for the scaling and the significant growth of the hydrogen market that we believe is necessary to achieve deep decarbonization goals. However, for that to happen, it is clear that policies are needed to support hydrogen market development, but specifically the inclusion of nuclear energy in that market. And to that end, we wanted to illustrate on this slide what we've been working on as part of the policy group in the white paper. So you'll see on your right, the hydrogenmap.com. That's actually a project that Pillsbury had independently put together to demonstrate all of the what we think are real hydrogen projects that are taking place all over the world. And there are 200 of them, and we're actually in the process of updating the map. There are now more than 300 projects for which actual commercial contracts have been signed, and there's real money, real participants, real interest in proceeding. If you take a look at the map on your left-hand side, you will see that this is a map of the hydrogen strategies, which includes all sorts of government support, whether it is a roadmap, it is a policy, it is a strategy, or it is simple financial support for research and development and or commercial projects. And looking at those maps side by side, you will see that the hydrogen projects are happening in those jurisdictions where there is some form of government support. So the two are interlinked. Let's go to the next slide. From this, we take a look at the jurisdictions that have some form of support. And we take a look at which ones have actually either explicitly or implicitly included nuclear hydrogen production. It is not all of them, but it is quite a few countries. They have recognized the value of nuclear in producing hydrogen with zero carbon fuels more broadly. And most of these jurisdictions have explicitly included nuclear in their hydrogen strategies. In some of them, you've had nuclear hydrogen production projects and pilots actually outside of the strategy, despite not having kind of an all government focused strategy. And those would be projects in China and Brazil, which both have pilots. In China, there's more focus on advanced reactors, small modular reactors, high temperature hydrogen production. In Brazil, you actually have a project for the production of hydrogen at the Angra nuclear power plant, which is happening today and has happened for quite a long time. But now there's an effort to commercialize that hydrogen. And you have an example of Finland, where there is no government strategy, but there is nuclear hydrogen production and commercial plants. But you see that those are the outliers, the ones that don't have a government strategy. Most of these efforts are being driven by some sort of government support. Let's go to the next slide. So we're going to give some examples of where countries have included hydrogen, nuclear hydrogen production in their overall hydrogen efforts. One good example is the US Infrastructure and Investment Jobs Act, also known as the bill that was passed last year in November. And that is a very big package. $9.5 billion of that 1.2 trillion is dedicated to hydrogen. 3 different areas, the main one being $8 billion for 4 regional hydrogen hubs. And the important part here for nuclear hydrogen production is that the bill specifically recognizes that at least one hub must demonstrate hydrogen production from nuclear. And I emphasize the words at least on one hub because we're likely to see not just 4, but potentially as many as 8 hubs or even more. And let's go to the next slide. As part of the regional hydrogen hubs project, the DOE conducted actually 2 requests for information. And the initial one was really more data gathering where some of these potential hydrogen hubs may be. And it's worth noting that the way the DOE is looking at this is not necessarily our typical definition of a hub when people think about an industrial facility or cluster of industrial facilities in a certain city or in a very specific limited geographic area. These are regional hubs that may include as many as 1 or 2 or even 3 states. And really a network of infrastructure within those states on the production, the transportation, and the end use, with the ultimate goal of creating a national hydrogen network, an interlinked network. With that, the DOE has really, based on the initial responses, has looked at 9 different regions and potential hubs in those regions. And if you look, take a look at the slide and the check marks there, 7 of these regional hydrogen hubs can and probably will include nuclear hydrogen production. So that's where the emphasis on at least one hydrogen hub will include nuclear comes from. And the types of nuclear hydrogen production are also potentially diverse here. So in some of these states, you have significant number of operating facilities that can produce hydrogen, that are using their existing capability to produce electricity and or heat. But you also have the potential to produce hydrogen from small modular reactors for example, like the Utah NuScale project that is taking place now that should be operational by 2030, and maybe some of the other projects that are currently being co-developed by a number of participants with some DOE support. So significant opportunities for nuclear hydrogen production there, and recognized and specifically included in the strategy. One other legislative instrument that's not on the slide because it hasn't passed yet is the Build Back Better Act, which is a very significant funding package that is still pending in the legislature of the United States. And one key element that it includes is a production tax credit for nuclear hydrogen production. As we scale, even with a very dense source and baseload source like nuclear, there still needs to be some investment as far as costs, because we're trying to bridge the gap between the current gray hydrogen market, fossil fuel produced hydrogen, which we think today is $1 per kilogram, although that could be a different number given the natural gas prices today and for the next decade, but that's the number that the DOE has set out. And the cost of producing hydrogen from some of these alternative sources through the electrolysis process, which may be higher than that, that production tax credit looks to bridge that gap, to really facilitate and catalyze these zero carbon hydrogen production projects. And it's worth noting that because of the technology neutral approach and the focus on greenhouse gas emissions, nuclear under that production tax credit is actually eligible for the highest tier, which is $3 per kilogram, which would be the same as renewables. And that's the approach that we'd like to see in a nuclear hydrogen initiative. Next slide, please. The UK is another jurisdiction that has put together quite a comprehensive hydrogen policy framework. They have included both near-term goals to 2025, as well as medium-term goals of producing 5 gigawatts of low-carbon hydrogen by 2030, with the idea to rapidly expand after that. A key part of this is the UK low-carbon hydrogen standard. And that, once again, similar to what we're seeing in the US, is a technology neutral approach focusing on greenhouse gas emissions. And it specifically, it includes nuclear, recognizing the low carbon value of nuclear as a hydrogen production pathway. It also includes 2 important business facilitation vehicles. The first one is the Net Zero Hydrogen Fund, which provides 240 million British pounds up to 2025 to cover the CapEx costs of these new projects. And then in addition to that, similar what the DOE is trying to do, the US government is trying to do with the production tax credit, there is a low carbon hydrogen business model that the UK has put forward, which is similar to the contract for difference mechanism that many of you may be aware of in the UK and other jurisdictions, trying to do that same thing, bridging the gap between the cost of gray hydrogen and the cost of clean hydrogen produced through some of these other sources through this contract for difference mechanism, and including some very specific requirements there, really focusing on scaling and ensuring that these low carbon hydrogen production projects are real. We've got a low carbon hydrogen agreement, and you have some conditions where the producer has to demonstrate that they're committed to the project and the project is actually going to happen. So very good mechanisms there in the UK that we think will be very helpful to scaling hydrogen production and specifically ensuring that nuclear plays an important role in that. Let's go to the next slide. Canada also has a hydrogen policy framework that was issued in December 2020. Similar to the US and the UK, they specifically included nuclear hydrogen production in that framework. They have looked at both production of existing reactors as well as production from small modular reactors. And they were looking at some of these new processes, such as high temperature electrolysis, and recognizing the value for nuclear. Unlike the US and the UK, Canada does not have a business model portion of this or financial aspect, but that may be something that's developed at a later time. Let's go to the next slide. So these are examples of 3 jurisdictions, but there are quite a few others that are developing or have already developed hydrogen roadmaps. And we think there needs to be more specific incentives and mechanisms in these roadmaps to ensure that the hydrogen market can effectively scale up and also ensure that nuclear can contribute to that. And with that end, in the white paper, we have set out a number of incentives and mechanisms that we think will work across various jurisdictions. And if we go to the next slide, I'll try to quickly summarize them. And for those of you who want to read more, please take a look at the white paper on the website. And also let us know if you have any ideas, because this is intended to be a living document, and we welcome other thoughts and other proposals. So as a baseline, we'd like to see hydrogen plans and roadmaps and strategies to be technology neutral. We'd like to see an emphasis on greenhouse gas emissions rather than a specific focus on a technology, on any one technology, because we think that the color scheme is not helpful. It potentially disincentivizes production processes that can in fact be crucial to making this market a reality. With respect to the policies and plans that have specific technologies that are listed, we do think nuclear needs to be expressly included as a zero carbon hydrogen pathway, and where you have very specific goals and metrics for hydrogen production, we think we should have those for nuclear as well. So we see some of these roadmaps, for example, X number of kilograms of hydrogen produced through, let's say, solar and wind. We'd like to see something very similar for nuclear as well. And to the extent that governments are focusing on hubs, those hubs should also include nuclear production facilities, both existing ones, as well as potential new technologies. Research and development is very important. So we have 3 different pathways for nuclear hydrogen production. One is low temperature electrolysis, which is something that we can do today because of the high TRL of electrolysis technologies and existing nuclear power plants. But we'd like to see specific targets, funding targets to get those projects off the ground and incentivize both the producers as well as the electrolyzer manufacturers. We are very excited about the potential of nuclear hydrogen production from high temperature electrolysis. And we'd like to see specific reference to advanced reactor hydrogen production. And then also lower TRL level, but very exciting, is thermochemical hydrogen production. On the incentives, we'd like to see both production incentives and end user incentives as far as tax credits, financial incentives, whether loan guarantees, the CFD type models, tax incentives for offtakes. And last but not least, we think government procurement is very important. Government has really taken an active role in decarbonization through its procurement models, and we think this also should be applied to hydrogen. So governments should preferentially buy products made through the use of low carbon hydrogen, including nuclear hydrogen. Thanks very much for this.
Thanks, Alina. Very comprehensive, and Carlos, really amazing progress you guys have made with the initiative. So I think we're kind of running over, but I think we have time for one question. And I think if you guys want to both quickly answer about the kind of challenges that you see in scaling nuclear hydrogen production, and maybe some of how you're thinking we can address those challenges. But we have to be kind of quick, so maybe 1 minute answer each or something like that.
Absolutely. Maybe I'll start and then turn it over to Carlos. We think just like any industry, the nuclear industry, sometimes it is waiting for certain incentives to be developed before it jumps in. So with today's industry, a lot of that is electric utilities, right? And these electric utilities have set business models. So developing new business models can be a challenge for some of them. And we think specifically that's why some of these incentives are really needed, is to demonstrate that there is government interest in supporting these projects. I think that's one key challenge that needs to be overcome. And I'll turn it over to Carlos for others.
Just to round up, I guess from a technical standpoint, I think we've seen a lot of demonstration projects already ongoing, as we mentioned, and I think we need to accelerate those to, I guess, prove to the market that this solution is a viable and it works, and it's all that we say it is. So to the extent that we can accelerate these demonstration projects across the world, I think that will help scale up as well.
Great. Thank you very much, both of you. That was great. I will now, you can switch off your cameras. Now we're going to hear from Thibaut Cantat. Thibaut is a research director at CEA, the French Atomic Energy and Alternative Energies Commission, where he leads a research group exploring the conversion of CO2, biomass, and waste plastics to fuels and chemicals. He also serves as the leader of the Circular Carbon Economy program there. His presentation will cover the scope of approaches explored at CEA to develop a carbon circular economy. Welcome, Thibaut.
Thank you very much. Hello, everyone. Thank you, Eric, for the kind introduction, and thank you for including me in this webinar. It's a great pleasure to present what we're doing and try to develop towards a carbon circular economy. Next slide, please. Okay, so the reason why we're focusing on a carbon circular economy is because when we look at the French energy system, in terms of the consumption of primary energy in France, which amounts to about 3,000 terawatt-hours, it relies, of course, on nuclear energy because our electricity is mostly based on nuclear electricity. But we also use a lot of fossil carbon resources. About 55% of our primary energies comes from carbon, and especially oil, coal, and gas. And when we look at the utilization of those carbon products, most of them, like a third of those carbon products, they cannot be substituted by carbon-free alternatives, such as electrification technologies, hydrogen, or battery-based technologies. Meaning that we still, in the future, if we aim for a carbon neutral energy mix in France, what we need to have is about 500 terawatt-hours of carbon-based products that we still need to produce in the long run from renewable energies and low carbon energy sources. And that's mostly to ensure that we still have liquid fuels for long-range transportation, but also that we can still produce materials which contain carbon in their structure. For instance, steel, cast iron, cements, and other chemicals. And I mean mostly plastics, agrochemicals, and solvents. Next. Next slide, please. Yeah, thank you. So the reason why we are utilizing so many carbon products, of course, is that because the chemical energy which is stored into those carbon-carbon and carbon-hydrogen bonds is extremely dense, and this is why we use a lot of liquids, but also gaseous fuels. And overall, in the world, about 85% of the world energy portfolio comes from fossil resources. Again, oil, coal, and natural gas, which we refine into fuels, and the side products, they go into petrochemistry. Next slide, please. Of course, at the end, all the carbon atoms, they are mineralized, meaning that they are oxidized and they accumulate in the form of carbon dioxide in the atmosphere. So coming from there, of course, we could capture and store carbon dioxide, and that's what we call CCS, carbon capture and storage. So although we believe this could be a potential solution to cut out CO2 emissions in the atmosphere, we don't develop CCS technologies at CEA, simply because this will still foster a linear carbon economy where we will exhaust at some point either the fossil resources or the capabilities for the storage of carbon dioxide. Next slide, please. In addition, doing CCS approaches is not moving towards better energy efficiency in the energy system, because you can see in blue is the linear correlation, which is well established, that links the GDP, so the economic industrial activity in the world, with respect to the energy consumption. Of course, what we would like to do in the future is move toward a more energy efficient system and more energy efficient economies. So following the yellow line, where we increase the slope of this correlation, meaning that we can produce more goods, we can produce more activity with consuming the same amount of energy. Nonetheless, if we move towards CCS, because we will consume more energy just to be able to capture and store that carbon dioxide, we will actually lower the slope of this correlation, moving to a lower energy efficiency at the end. Next slide, please. So what can we do instead of just doing CCS technologies? Well, the legislation is trying to push us towards a more sustainable and more circular carbon economy. And in particular, in Europe, last year was published a new regulation package, which is called the Fit for 55. And within this package, there are new targets which are set especially for the aviation and for the maritime transport. If you look at the aviation, for instance, the package sets binding targets per volume shares for renewable fuels of non-biological origins, meaning that we need to produce by 2050 about 28% of the fuels which are used in the aviation for traveling inside Europe. About 28% of these fuels should come from CO2 capture and recycling using low carbon energy sources. Next slide, please. So to be able to do that, of course, you need to provide some energy. So those are the green arrows that you can see there. And for instance, starting from carbon dioxide, which is captured either at point sources or directly from the atmosphere, convert CO2 back into those desirable carbon-based chemicals, such as fuels, polymers, etc. So of course, we need to bring some energy to activate, cleave, and reduce the CO2 molecule. Although maybe sunlight is the most abundant one and the cheapest one in the long run, this is a large and a tremendous change of paradigm compared to what we're doing actually today, where we extract chemical energy from the soil. So in the short term, what we see is that first, sunlight will be converted to electricity through wind technologies, photovoltaics, and electricity utilized for the electrolysis of water and promotes the formation of green hydrogen that can be used to convert CO2 into chemicals and fuels. So those are the hydrogenation pathways. In the longer run, electrolysis is of course a good opportunity to convert electricity and store the energy and electricity into chemical bonds. And of course, nuclear energy is a good opportunity to valorize low carbon electricity and store it into chemical energy. In the longer run, the direct conversion of sunlight into chemical energy is a possibility. And this is also something that we're actually doing naturally, because biology through photosynthesis is already actually capturing CO2 directly from the atmosphere and photons directly from sunlight to grow biomass. And that's why, in our view, a carbon circular economy is not just about CO2 conversion, it also comprises biomass conversion, because we see biomass already as a source of renewable carbon, but also a source of renewable sunlight, which is already stored in the form of biomass. So that's why we have a program devoted to carbon circular economy, which is a collection of all the technologies which are able to convert CO2, but also derivatives such as biomass and carbon monoxide coming from the industry, and to convert CO2 and these derivatives into useful products using, of course, low carbon energies, and those include nuclear energy and renewables, in order to achieve a carbon neutrality, of course, with a positive environmental and societal impact. This is why we have cross-cutting challenges, looking at the impact analysis on soils and climate, doing LCA analysis to make sure that we don't create new problems, not on carbon, but on different elements, etc. Next slide, please. So the way we see the value chain for those carbon circular economy comes first from the collection of the resources, because we need low carbon energy sources such as electricity, but also hydroelectricity, solar, wind electricity, or nuclear electricity, plus, of course, the carbon source, which can be CO2, but also derivatives such as biomass, waste plastics, solid waste coming from cities, etc. The idea at the end is to convert those resources into key molecules. Those could be gases, liquids, and solids for the main two sectors that we identified, which are the energy sector and chemistry, those two sectors which are really difficult to decarbonize. And the key element into this value chain is, of course, the way you produce, the way you transform, the energy sources and the carbon sources. So we have organized our program along 3 lines. The first one is about thermocatalysis and thermoconversion, where CO2 or biomass are converted with dihydrogen as a source of chemical energy. Electrocatalysis and photoelectrocatalysis is a research and development program aiming at the conversion of CO2 together with water in the presence of electricity or directly sunlight, for instance, to produce solar fuels. And finally, because we have expertise in biology, we also have a research line dealing with the conversion of CO2, water, but also biomass directly using sunlight into those useful gas liquids for the energy sector. Next slide, please. So just to give you a quick overview of what we're doing in terms of the different research projects and the different strategies and challenges we have identified along those 3 research lines. Here's an example of what we're doing on thermocatalysis and thermoconversion. For instance, to convert CO2 in presence of hydrogen to methane. This is a highly exothermic reaction, so we need reactors which are able to deal with the increase of temperature along the conversion of carbon dioxide in the presence of hydrogen. So we have a research program dealing with the formation of methanation units and reactors which are dedicated to CO2 conversion. We also look at the conversion of biomass using different kinds of technologies. Here's an example of a fluidized bed converter for the conversion of biomass, but also solid waste. And so we have different strategies aiming at the development of conversion paths going from CO2 and biomass to fuels and chemicals. We explore the conversion of CO2 from the design of new catalysts to the development of reactor and processes. And of course, we develop new reactor architectures to shorten the value chain of CO2 conversion, trying to convert directly CO2 and hydrogen to useful chemicals and fuels. Of course, the challenges are the challenges which have been identified, I think, from the whole community, especially a difficult economic balance because of the competition with fossils. And we need, of course, the utilization of green hydrogen to be able to utilize those technologies. And this really questions how the carbon value chain will compete with the hydrogen value chain or how they will complement each other. Next slide, please. In terms of the research and development projects in biology, so what we do is, of course, we utilize the basic mechanisms of photosynthesis, which you can see in the upper left corner, where CO2 is converted together with light by the photosynthetic machinery. So our program aims at developing and optimizing different strains by genetic engineering and synthetic biology in order to grow microalgae, but also cyanobacteria in open and closed reactors in order to produce biomass. And the biomass can be carbohydrates, but also different kinds of oils, which can be then refined and used as drop-in fuels in the industry. Next slide, please. The photoelectrocatalysis path is super challenging because what we do is mimic photosynthesis by using new kinds of materials which are able to capture sunlight, convert photons into electrons, and then the electrons are stored in the form of chemical energy by reduction of carbon dioxide. So here we are really at a much lower TRL, designing the different cells, working on the performances and the robustness of the materials in order to target the production of specific chemicals and fuels. Next slide, please. Or we can drop this slide and go to the next one if I'm running out of time. Okay, so here comes really what we're trying to do since a year. It's really to start and see how nuclear energy production can provide electricity, but also heat for the production of sustainable fuels. So we have 2 research lines looking at very specific case studies for low carbon industrial complexes, which we want to decarbonate, especially complexes where we have chemical industry, so an activity that is very difficult to decarbonize. But we are also looking at optimized chain values for the production of specific commodities and especially sustainable fuels for the aviation. So we have numerous questions we are trying to address, especially looking at what's the best nuclear reactor technology and architecture to provide heat and electricity, depending on the kind of carbon source that we want to convert? Is it CO2? Is it biomass? Do we want to convert together CO2 and biomass? What's the source of carbon dioxide? What is the energy mix that we use? Are we resulting on the dedicated reactor, or do we rely solely on the grid, or on a mix between the dedicator, the grid, with the possible penetration of renewables? So all those questions we are trying to address. And of course, looking at the output, what are the different utilities that we want to provide? Is it just fuels or just captured CO2, water, clean water, different kinds of molecules for the industry, but also heat and electricity. So that's the end of my presentation. So you can see that we mostly have questions at present that we're trying to answer in the next years. Thank you very much for your attention.
Thibault, thank you very much. Yeah, I think this couple of things you raised are really worth pointing out again. And one of them, I think, and this comes from our work as well, is that co-production of valuable products turns out to be a very attractive business model. And this is something that when you look at the traditional chemical industry, they do all the time.
Exactly. Yeah.
And so I think one way that your work points for us is to go beyond just the kind of simplistic, like one reactor makes one product and sells to one customer, but beginning to think in this more integrated way. So with that in mind, do you have a sense of which sectors in France are going to be the kind of early adopters for this kind of circular carbon synthetic fuels that you're talking about?
Yeah, that's a really good question. So because our electricity is already mostly decarbonized, thanks to nuclear electricity, the question for us is not so much of trying to decarbonize further the electricity, but we need to start and tackle right away the decarbonization of much more difficult to decarbonize sectors. And in particular, for the production of sustainable fuels, so what we see is really the aviation is a really good driver. Mm-hmm. And at the same time, it's also questioning us about, is it the best strategy? Because we know that we're going to have to decarbonize the aviation, but also the maritime transport at some point. But in the short run, we all know that we're going to need a lot of low carbon electricity. And we need to look at what is the best use of that low carbon electricity. Is it to decarbonize the most difficult sectors, or should we have a more practical approach in the shortest run and try to decarbonize, for instance, the steel industry, which is a bit easier to decarbonize, but this one does not necessarily need carbon-based and sustainable fuels. Mm-hmm. So I think and that's for me the most difficult question to answer right now, is like, we need a trans-sectorial view of the best use of low-carbon electricity. And that is a bit lacking in all the strategies that we see, because they involve very different sectors. And we will have to prioritize at some point. So yeah. Our approach is to say, we're gonna need some sustainable fuels at some point, maybe in the midterm or longer run. So we need to try and start tackling those processes first.
Okay, great. So we do have a question from the audience about the Sabatier reaction for methane production.
Yeah.
And do you still see that as a feasible path, or do you see the bio route as more interesting? And I'd like to just add a kind of a comment to the question, which is that I've been doing a bunch of work with Charles Forsberg at MIT, looking at actually the integration of biofuels and nuclear energy, both as you point out, the supply of the heat, but what people may not realize is that 2/3 of the energy for fuels production, classical biomass-based fuels production, comes from oxidizing carbon that's in the biomass. And so you're actually throwing away 2/3 of the carbon product when you're making fuels in the biofuels in the traditional way. And one of the prospects of using nuclear energy is that you basically get all 3/3 of the carbon in your product, that because you'd be getting your heat and your electrical energy and your reduction energy from the nuclear energy input. So I think, that's I think the way you see the bio route is maybe different than the traditional bio route.
Yeah, we really think along the same line. So if we take the example of methane to answer the question, so the Sabatier reaction is combining CO2 and hydrogen together to produce methane. And we should not oppose this production of methane with the bio routes, because as you said, in the bio routes, the methanization reaction, where you take biomass and you convert it into methane, that produces also about the same amount of carbon dioxide. And we should not lose that carbon dioxide because it's coming from biomass. So it's biogenic carbon, and the capture of CO2 has already been performed. So let's not waste it. And for instance, we could complement the methanization reaction with the Sabatier reaction and converting all the carbon atoms together, producing 100% of methane instead of 50% methane and 50% CO2. So they go along the same lines, those two strategies, and they really complement each other.
Great. Well, Thibaut, thank you so much. A great presentation and very exciting work that you guys are doing there. I look forward to visiting.
Thank you, Eric.
So next we have Troels Schoenfeld. Troels was raised in a family and in a community where literally everyone that he knew was against the idea of nuclear. And when he started studying physics at the Niels Bohr Institute of the University of Copenhagen, he realized that many of the arguments that he had heard and maybe believed against nuclear power were not actually based on facts. And this led him to finish his PhD in nuclear technologies and neutronics. And then together with other colleagues in Copenhagen, also all with PhDs, he founded Seaborg in 2015. So Troels will introduce us to the vision of Seaborg, which is barges with up to 800 megawatts of energy production from compact molten salt reactors, and also their vision for how those can be part of the synthetic fuels economy. Troels, please.
Thank you. Hi. Yeah, as it says here on the first slide, we are rethinking nuclear. So let me handle that up front and say, oh, actually, it was on the front page, but okay, let's go here. But rethinking nuclear, what we see is an industry in distress, where historically all research and basically also all new build has been financed by governments, and where the regulatory system is stuck in traditional nuclear. So we need a quite massive disruption to get nuclear back online, basically. And as physicists, we also look at the fact, and when we look at the climate reports and the data on CO2 release and other pollutants, it actually looks quite aggravating, like to a level where it's kind of irresponsible to get kids at this stage, which is not a planet we can live in. So we basically have to go out there and do something about these problems. UN says that we need nuclear, and I think a lot of us think, okay, then we need it here in our small pond, but the world is a pretty big pond. So we're in Europe. In Europe, we don't support nuclear from a European level. We are in Denmark. Denmark is the first country that banned nuclear power. So we are very anti-nuclear in Denmark. So how do we do this? And what we did is we looked around the world at which issues out there. And one pretty massive issue we found, which I think is kind of interesting, is around the equator. Most countries are developing countries there, but you actually have a belt around the equator where there's virtually no wind. This is just how meteorology works. Simultaneously, when you run around the equator, you will find that there are two kind of natures there. One is desert. In desert, you have sandstorms, so solar panels doesn't work. And the other biosphere is jungle, where you have rainy days and monsoon seasons. Thus, solar doesn't really work. You will also find that around the equator, you have almost no high altitude rivers. So hydro is kind of off again, and the geothermal power is limited. One such example is Southeast Asia, where, well, by 2050, there will be around 1 billion people living there. And they cannot access renewables at any scale. So they are basically stuck with coal, gas, or nuclear. in today's pathways, they are not allowed to do nuclear. So they have a pretty big problem. But that's the problem we want to go in and help them handle. But to do that, we need to rethink nuclear. So that's just to say the scale of this issue is actually massive to an extent where there's 1 billion people on this planet that has enough electricity today. And if we want to get the rest of this planet into a prosperous lifestyle, then we basically have to 8 or 10 double the amount of energy on this planet. And half of that population doesn't have access to renewables. So the problem is pretty massive. Anyway, if you can go to the next slide. So here, this is our fundamental hypothesis, because since I was a little boy, I was annoyed that the politicians kept talking about we should stop pollution. The first agreement to go to zero carbon dioxide release was actually signed by most countries in '92 in the Kyoto Agreement. And today, if you look at the data, we haven't begun yet. So our fundamental hypothesis is if we want to move this, if we want to decarbonize, it has to be two things: cheap enough and scaling fast. Where fast, looking at the data, fast is a ridiculous speed. Ridiculous. It's completely out of this world speeds and scaling we need with future technologies to reach our targets. Cheap enough is actually fairly easy to handle, because that doesn't mean that we should hit a magical 5 cents per kilowatt hour price or anything. It just means that in the market we engage in, there's a strong business case where the manufacturer are attracted enough that they want to scale the supply chain, and where the investors are attracted enough that this is the preferred choice, and where the end user actually wants to offtake the electricity. So the cheap enough is just, well, it's no price. It's just cheap enough depending on the market. So next slide, please. So before going into who we are here, I want to just to what we do. I want to just handle who we are. So as I said, no public funding in Europe. So we are privately held and privately funded company. That's actually a pretty strong point for us, because it means that we have learned to think very commercially from day one, and we cannot just depend on subsidies or government grants. We have to go and find a business case that is sustainable. No government help there. So that's a really strong point. By now we are, I think, actually 120 people, and we are still scaling to 150 within this current funding round. We are people from, I believe now 27 countries. We grow very fast these days. It's actually really amazing to be part of. I can tell you that 1.5 years ago we were 22 people. So being 120 is quite far from that. We have our headquarters and labs here in Copenhagen. We have built state-of-the-art labs, a few hundred square meters, I think 400 square meters now. We have 1,200 going into construction these days, so quite big labs. Then we have business offices in South Korea and Singapore. And just to attach a comment to that, I think in this meeting we are talking about what can Europe do, and when we say Europe, we mean France, because they are pro-nuclear, and maybe UK. When we say the Western world, we also include US. I think this meeting is very revolved about US and what can they do. But if you are in US, France, or UK, you will be absolutely locked down by export control. So it's very hard for these products to go to the developing world. That means we have an upside in not being part of the established nuclear countries. So we can actually go to these countries with products. So that's what we're focusing on, very much so. And that's very hard, because there's a lot of challenges there. But this requires South Korea and Singapore. Then we have partnerships in the shipyard. So we're not just a small company. We actually have Samsung behind us as a partner. They are not a small company, and it's hard to work with when we are a company of only a little more than 100 people. We also have huge industrial players in the nuclear industry and heavy industry. And remember, these are not subsidized to come in and play with us. These are companies that does this because of the business case. Of course, we also have a lot of academic relations. But next slide. So what are we doing here? Yeah, we are. When you're in a developing country, it can be hard to educate a workforce to build these units. So what we want to do is actually use established supply chains. There's plenty in Siemens know how to build turbines for high temperature steam. Samsung knows how to build barges in our case. So use these established supply chain components and then mass produce these products and ship them to the areas where they're needed. So that's what we want to do. And what you see here is a 200 megawatt, a 400 megawatt, and a 600 megawatt reactor. There's also an 800 megawatt unit we can do. Quite a big disruption to the energy industry that we can bring by doing it like this is a from order to grid timeline of 3 years. Today in the energy market, not just nuclear industry, but in the energy market, you have to plan 15 years ahead. With nuclear, you probably have to plan 25 or 30 years ahead. But 3 years from order to grid is a game changer there. And then we want to commission these reactors fully at the shipyard, which is also a little bit of a smart move. But let me just skip to the next slide. Okay, yeah. So what we're doing is actually a molten salt reactor, and to explain it a little bit in layman terms here, I brought a couple of pieces of fluoride salt here. Here's I don't know if you can see the camera, but here's a couple of pieces, and these are found on the beach in Denmark actually. Quite beautiful rocks. You can buy them in crystal shops because they're also good for your spirituality. But we use them for nuclear power. The magic behind the fluoride salts is that we can take this salt, we can dissolve the nuclear fuel into it, we can melt it. It melts around 500 degrees centigrade. Then we can pump it into a nuclear core and generate a lot of energy. And when you create that energy in the nuclear process, you have these fission products coming out. Those are the dangerous radioactive elements. In a conventional nuclear reactors, these are contained as gases, kind of like in a brick of an oxide lattice, but it's kind of like it's in a brick. But if that brick is opened up in an accident, then these gases come out, and gases, highly radioactive gases, are quite dangerous and quite hard to handle when they get out. So that's what actually is the cost driver of nuclear, that you have to contain this gas no matter what happens. But in a fluoride salt reactor, the fluorides, they react with these fission products to form new fluoride salts. And as I said before, the fluoride salts simply behaves like a rock in nature. So having in case of the extreme accidents, having a gas cloud coming out versus having a liquid rock that solidifies coming out, very, very different. Both are radioactive, but in one case, your measure is to not breathe, and in the other case, your measure is to clean up. And that's just a way more handleable scenario for accidents, meaning that we can make a much simpler design, which saves us money and makes this a very cheap technology. So that's the magic behind fluorides. But fluorides are not easy to handle, so we have built all these state-of-the-art labs to do it. Next slide, please. So again, to simplify it in the public, I say we have a reactor that cannot melt down or explode, cannot release gases to air or water. And that actually also goes when Putin drops by and drops a bunker buster into the center of the reactor and splatters this everywhere. Doesn't go anywhere but that. It just stays and solidifies. And then it cannot be used for nuclear weapons. And as any nuclear reactor, we have a very high level of supply security. Let's go to the next slide. So here you see an illustration of the barge. So we plan to have 2 reactor modules on the barge here installed in front. They supply high temperature steam. This is a high temperature reactor, so you get high quality steam out. It goes to a turbine. That turbine generates electricity. The reactors operate for 12 years, and then we install 2 new reactors and operate for an additional 12 years. It's as simple as that. And then, yeah, let's just go to the next slide. Yes, that one. So we imagine our supply chain, and supply chains are actually quite important for the scaling. So, and as a startup, you want to really be as lazy as possible. So you should have as small a footprint in the supply chain as you can possibly have, but you cannot remove your foot entirely from the supply chain because you need to maintain your IP. So we imagine that existing partners, we actually have partnerships with most of these players. They can deliver valves and pumps and all of these components to us. We assemble them. We ship them to Samsung, who does the heavy lifting and installs a turbine on a barge, our reactors on it, ramp it up and take it to the grid. And since we're talking hydrogen, I think everybody's talking about Power-to-X, at least in Europe, but we are calling it Power plus X. because with wind, you're getting either power, and occasionally you get too much power, and then you will get some X. But with nuclear power, you actually get both. You get a lot of power, and you get the X at the same time. And I think the future requires both. And that's nuclear's role in the future, I believe, to be able to supply stable power while producing ammonia or whatever it is. Then also, I would say we include the recycling in this. So we are on a barge, meaning that the recycling is actually on a global stage, meaning that we can recycle via a tender. So who can do it cheapest, who wants the fuel? Not this as it is today, it's a government thing. And if they don't solve it with the one company that can do it, then they will have to retire from the next government. So that's actually a pretty big problem. Next slide, please. Next slide. Yes, please. So okay, that's something is wrong here. But anyway, so we are saying global licensing approach, and I said you cannot build nuclear reactors in developing countries. I will say that that's because in developing countries, who trust a regulator? So the way we solve that is by actually using a maritime framework where you take the same rules and regulations as you would onshore. It's the same, it's the exact same authorities and the same rule books, but you are regulating it internationally. So if a developing country wants this, a developed country can come in and say, we actually ensure that this lives up to the standards, and we put our flag on it, and we do the inspections to ensure this. That's an enabler for these developing countries to get into nuclear today. And in July 2020, we were the first to get a commercial approval of any kind of advanced reactor, which I'm quite proud of. Then go to the next slide, please. So this is where I'll finish. I'll say develop in Denmark, we're good at developing. Build in South Korea, they're good at building. And power the world, because they are pretty good at spending power. And I just want to draw your attention to the corner here, or the subtitle. 200 power barges per year by 2035. Magically, this is actually something we can do with existing supply chains. Also kind of magically, and unfortunately, this wouldn't cover the planned expansion of coal and gas in Southeast Asia. So this is existing projects we can replace with this. And amazingly, 200 power barges a year would correspond to roughly 5 times the global wind production to date. So this is in 1 year we can do that. So we can reach these insane scales, but even with those, we're not getting to win the climate fight alone. So we need a lot more. Thank you. Next slide. It says thank you.
Troels, thank you very much. And yeah, our numbers for the number of terawatts that we need to fully decarbonize the oil and the gas and the coal and everything like that is somewhere between 10 and 14 terawatts.
Yeah, it's insane.
Yeah, and I think this is this is a really great. I love what you're doing, and I guess maybe talk a little bit more about sort of inherent safety and what inherent safety means for the scalability and for the for example, one of the problems that you have even in the US in the conventional reactor industry is that all the people who work in the nuclear plants are getting old and they're retiring. So you have this kind of personnel problem, right?
Yeah.
And if you need very, very specialized people, then you have a kind of a new constraint in your scaling challenge. So maybe you could talk a little bit about how you guys are thinking about this type of aspect of scalability and how your technology paradigm might help with that.
Yeah, but the scalability is as I said, central for everything.
Yes.
So we're thinking it into all aspects. How would you train people? How would you operate these barges? A really good example is that the barge, it has this control room where you have cabins, and in those cabins, I mean, when you have cabins, you can suddenly operate this as an oil rig, like we would operate an oil rig. The smart thing about operating it as an oil rig is, while that gives you expensive personnel, you can ship them from all over the world. So you don't have to depend on local education into operating this, or for people to be expats and move to a region. They can just fly in, do a 2-month or 6-week or whatever operation shift, and fly out again for 6 weeks of vacation. So that's, I mean, you have to think scaling at all levels, and we're very firm on this, picking supply chain components that are existing. So in the nuclear industry for today, you need a specialized turbine because it's low temperature steam. So that's a very specific device with low efficiency, and where you need to do specific research for this if you want it for your nuclear reactor. And so everything is specialized for this. So instead we said, no, actually, let's just go to this 570 limit that is the current standard for steam for coal power, because then we can make use of the turbines that is today built for coal power plants. The reason we picked 200 megawatt is because that's actually often the size of these turbines. So that's where the price saturates, at least. So picking components that are already there in existence. Of course, the molten salt reactor itself is not in existence, so there we have to do something new. But minimize the need for new development and make sure that the supply chain is there when you are done developing. That didn't answer the safety part, but if you ask about that again, I will just answer that.
Yeah, I guess the reason I wanted to ask about that is because although you've made it clear in your kind of very quick presentation about how different this is from your grandfather's, light water reactor, I think people still have a kind of a picture in mind when you say a nuclear reactor, and they also have certain kinds of reflexes about what it means to kind of make sure that that's safe and to inspect all the things that need to be inspected and so forth. And these things really limit when you kind of have all that stuff sitting in there in the way, you really can't have this kind of expansive rollout or expansive image of what you're meeting. So I think if you could maybe just elaborate a little bit about how that not just safety, but kind of all the operational and things that are kind of difficult and make nuclear difficult to scale, that you may be able to address some of those.
Yeah, but I think the safety is central there, because one of the problems with nuclear power is where to put it. It should be 250 kilometers from any big city. Okay, where is that? I mean, where do you need a gigawatt of power and you're 250 kilometers from a big city? It's just not that common. So that's actually quite fundamental, that you can get into the harbors, not to the beautiful part of the harbor, but to the industrial harbor, and just shelter there in shielded waters behind the docks. But in order to do that, you need the safety, right? Because the issue here is that a nuclear power plant is something people fundamentally don't really understand. I mean, us experts do, but the general public doesn't. When you look at a wind turbine, you're like, yeah, I know the wind. I had one of those when I was a baby in my small trolley there. But when you look at a nuclear power station, what is going on in there? There's some complex words going on, and it's dangerous. But it's not so much about the public opinion here. It's more, there's a reason for people thinking that. And that is because we have a history in the nuclear industry for actually putting compliance above safety, and then letting compliance ensure the safety, which is a horrible approach, and then not taking responsibility. So we're like, oh, it went wrong because of somebody else, and actively saying that everything is dangerous. And why are we saying that everything is dangerous? Well, actually, it's a little bit funny. That's probably because it is dangerous. So it needs to be handled with care. So the change from having this radioactive gas that is a huge problem if it comes out, to having this salt that is stable in nature, is actually fundamental. Because when somebody bombs your plant down in the harbor, right? Okay, in the industrial harbor, if somebody bombs your industrial harbor, you probably have a problem as the city, right? Because somebody bombed your plant. But say you take a top modern bunker buster bomb and throw it straight into the reactor. This salt splatters into the harbor and onto the field. And your action there is to immediately close off that area, close off the harbor. You have to send robots down and pick this up because it's highly radioactive. But it's there at the bottom of the harbor. There's no risk to the city. The risk is contained within the fence. So that's just a fundamental change in the safety profile of this. I typically say that in the nuclear industry, you have to reduce the likelihood to zero. Instead, we are reducing the consequences. And if you reduce the consequences, then you don't have to reduce the likelihood in the same way. And you can put it in a harbor, in an industrial harbor. So that's actually, safety is quite important for the scaling of nuclear power.
Great. Thanks. Do you want to say anything more about fuels, or this was about hydrogen and synthetic fuels? Do you want to touch on that, or?
Yeah. So I didn't touch on that on purpose because I knew everybody else would be talking about it, and then people get bored. But I would actually say that our basic business case is to provide 2/3 baseload power to a city and 1/3 to an ammonia plant. In our case, we have picked ammonia because when we look at it in the West, here in Europe and US, everybody's talking about hydrogen. All the politicians are talking about it, and that's where the subsidies go. But when you go to a more pragmatic corner of the world, like South Korea or Southeast Asia or wherever, the industry says, well, it's not going to be hydrogen because that's too hard to handle. It'll be something pragmatic like ammonia. And it seems like by now the shipping industry and the steel industry have settled on ammonia in the regions that are not subsidized for saying that it's hydrogen. And even in the regions where people are subsidized for saying the word hydrogen, it seems like the industry is behind the curtain saying ammonia. So we just went for ammonia. So we are a Power Plus X constellation. It's a really good case because when you have a city, you will need a baseload power. We can provide that. But when you have a city in a developing country, you will have, or in any country, you will have fluctuations in your power requirements. And that grid instability is actually really dangerous for the grid. So that's the highest value component of any grid, is to provide the safety net. So having the ammonia facility gives us the option to provide extra power when needed, or to dump power from the grid when needed. So it goes either way. So it's a very strong case to provide stable power with these X productions.
Fantastic. Thank you very much, Troels.
Thank you.
Now I'd like to introduce Chad Richards. Chad is the director of the Bruce Power Center for New Nuclear and Net Zero Partnerships at the Nuclear Innovation Institute in Ontario, Canada. The center works to demonstrate nuclear power's critical role in achieving a net zero future, both as a pathway to electrification of the economy and as an enabler of other low carbon technologies. Chad will discuss work underway at the provisional Ontario and federal Canada levels to leverage nuclear assets like Bruce Power Nuclear Generating Station in the production of low carbon fuels. This includes hydrogen strategies at each level of government and private partnerships that have been struck to advance clean fuels.
That's great. Thanks very much, Eric. Appreciate that introduction, and thanks very much to the Nice Futures Initiative, the Clean Energy Ministerial, and the Hydrogen Initiative for inviting me to speak at this webinar. I have the very difficult task of following an impressive lineup of speakers, so I will do my best to follow through and build on what others have already said. And as we like to joke around here, I'll try to keep it nice and light. I know I'm at the end of the webinar here, but we'll keep it light since we're talking about hydrogen. A little hydrogen joke. I'm sure my team is rolling their eyes already at that. But really, before we get into some of the content of what we're going to get in here today, I wanted to provide a little bit of context on who the Nuclear Innovation Institute, or the NII as we call it, is, and what the Bruce Power Center for New Nuclear and Net Zero Partnerships is as well. So at the NII, we are an independent not-for-profit based in Port Elgin, Ontario, up in Canada. We are right on the shores of Lake Huron, and we operate about a half an hour from the site of the Bruce Power Nuclear Generating Station. We're founded by a number of founding members in the nuclear sector here in Canada, ranging from Cameco in the uranium mining sector to Bruce Power themselves, to other suppliers across the supply chain in the nuclear industry here in Canada. At the Bruce Power Center for New Nuclear and Net Zero Partnerships, which is the program that I'm the director of, we really see ourselves as a bit of a combination of a think tank and an action tank. So we do a lot of original research and awareness raising projects on really the role of nuclear in that net zero a future that we're all striving for, as you mentioned, Eric, in your introduction. But we also do kind of at the action tank side of things is really to do specific decarbonization work in the region within which we operate, which is the Bruce Grey and Huron County region of Ontario here. So we're looking to actively partner with community organizations and other low carbon technology developers to really drive that decarbonization here at home. And we also look to actively promote partnerships with other low carbon technology providers, that spans kind of the clean energy sector, from hydrogen to renewables, looking at potential fusion, the potential for fusion here in Canada, and really building on the work that our former Center for Next Generation Nuclear had done to really advance this notion of new nuclear here in Canada. And it really is an exciting time when you look at the nuclear sector in Canada. It's really an exciting time to be working in the sector. Right now, nuclear in Canada provides about 15% of our country's electricity across the board. When you look at individual provinces, which we'll kind of get into in Ontario context in a little bit, that dramatically increases. We have a really robust supply chain supporting our CANDU fleet, and we're also advancing new nuclear technologies in Darlington here in Ontario at OPG's Darlington site, looking at a BWRX, a small modular reactor, and just this week, Saskatchewan announced that they would be moving forward with developing a small modular reactor build in that province as well. So really an incredibly exciting time for nuclear in Canada. And when it comes to hydrogen, that's good news. We have a long ways to go to get to find production opportunities for hydrogen, but really the role of hydrogen will be critical as we look to reach net zero. Our Canada's energy regulator said that in 2020, refined petroleum products accounted for 41% of Canada's end-use energy profile, and we really see hydrogen as having an ability to really offset a lot of those carbon-intensive practices using those refined petroleum products. So if we can move to the next slide, please. Maybe back one. So just kind of building on what the center itself does, we do that thought leadership and original research as a typical think tank does. So and really the equation within which we operate is really that nuclear plus X equals net zero. So nuclear is that fixed variable in that equation, and it enables things like, so for instance, in the case of this webinar, we're talking about nuclear plus hydrogen equals net zero. We've also done work on how baseload nuclear can enable energy storage technologies, which in turn can be used by grid operators to meet peak demand. And obviously, we'll kind of focus in on really nuclear's role in enabling that hydrogen economy that we all would like to see. And we have an example of that on the next slide, please. So really one of the things that we've looked at, we have tried to present things in really visual and accessible forms for people. So when we look at Canada's hydrogen ambitions and our goals by 2050, we're looking at potentially needing 436 terawatt hours of electricity to power, if we were to use electricity or electrolysis to produce hydrogen, and to meet that level of hydrogen demand. That's what we're looking at for electricity. So one thing that we did through the center here is look at through the former Center for Next Generation Nuclear was look at what does that look like in terms of land use, and really making that case again that this hydrogen economy that we're all striving for really needs nuclear. And when you look at the sheer number of acres that these projects would take up, it really makes that case again that nuclear has an absolutely foundational role to play in producing hydrogen. And that just this visual kind of presents it in black and white in that regard. Next slide, please. So the focus of my presentation today will be on more on the policy side rather than the technology side. I think we've had with Thibaut and Charles some really good overviews of technologies. Really in Canada, we have a very robust policy framework, as Alina mentioned off the top of the webinar, that is really enabling and really laying the groundwork for a really productive and really thoughtful hydrogen economy as we move forward. And two of those foundational pieces are the Hydrogen Strategy for Canada, which was launched in December of 2020. And Ontario, which is the province that we operate in here in Canada, Ontario's low carbon hydrogen strategy, outlining a bit of a path forward for the province here. And we'll get into how some of these strategies really see nuclear as a critical piece to enabling hydrogen production here in Canada. Next slide, please. So the federal government's hydrogen strategy, so the government of Canada really took the initiative to develop a pretty robust strategy. It's a rather lengthy document, and it's a bit of a living process. It's not kind of, you know, one policy paper that got published and then we're calling it a day. It really established a bit of a framework for how we're going to work on these issues as we move forward and really advance this strategy together with industry, NGOs, academia, lower levels of government at the provincial level, how all of these partners can come together and work within one framework to advance this hydrogen economy together. The strategy itself creates a number of working groups. So working groups being groups that are tasked with looking at specific subject areas within a hydrogen economy. So there's an electricity working group, for example, that's looking at not necessarily just electricity produced from nuclear power plants, but looking at electricity produced from all sources and how we can enable grid-connected electrolyzers to operate in the country. There's a transportation working group that's looking at end-use applications for hydrogen once it's produced. So whether that's, you know, from public transit to fuel cell vehicles, et cetera. But specifically, what was nice for the nuclear industry here in Canada was to have a specific nuclear working group established, and really that kind of was a critical piece to say that nuclear absolutely is that foundational piece of a hydrogen economy here in Canada. And then within the nuclear working group framework, that group was struck last year, and really what we have done since then is divide ourselves into individual task forces that are looking at kind of specific challenges to hydrogen production from nuclear assets here in Canada. And those task forces include things like the Production Opportunities Task Force, which I'm fortunate to have the opportunity to be the lead of, the Economics, Finance, Business Models and Policy Task Force, which will take some of what we do on the production opportunities side and really advance some of those business models, those policy frameworks that are absolutely critical to making sure these opportunities can thrive. We also have production processes task force, which would look at different ways that you can physically produce that hydrogen from the nuclear asset. So we'll get into some of that later, and some of the different applications for steam and thermochemical processes as well that'll be explored through that task force. And then an equipment and infrastructure task force, which again, the kind of the technology focused task force. So all that to say, it's a rather robust framework, and the individuals and organizations that work within this framework span from nuclear power plants themselves to academia, to NGOs like ourselves at the Nuclear Innovation Institute, to the government themselves, whether that's at the federal level or different provincial level partners as well, are kind of all involved in this policy framework to ensure that a hydrogen economy can really take off here in Canada. Next slide, please. So I mentioned that I have the opportunity to lead the Production Opportunities Task Force. And one of the things that we've been grappling with through that task force is looking at really nuclear's role in creating a clean grid. And I mentioned off the top that nuclear itself accounts for about 15% of Canada's electricity use here in the country. But in Ontario, we're really quite blessed with a very clean grid. And when you look at where that comes from, as the slide indicates, it's about 60% because of the nuclear sector here in Ontario. So really quite a substantial opportunity to leverage that and really have an opportunity to create green hydrogen from simply grid connected electrolyzers. It's really a really great starting point, and nuclear is doing the heavy lifting on that side. And that's something that our Production Opportunities Task Force has really flagged and made clear to that electricity working group as they move forward, that if you want to enable green hydrogen production from grid connected electrolyzers, then really you need to ensure that there's a solid green backbone powering that electricity grid, and that in Ontario's case, that's made clear through the contributions from our nuclear sector here. Again, we're fortunate that more than 90% of our grid here in Ontario is already carbon free, and we're looking to our independent electricity system operator here in Ontario is already looking at pathways that we can fully decarbonize the grid, so that when we are relying on these electrolyzers connected to the grid, that we know for sure that that's coming from green sources. So really a substantial opportunity, again, for nuclear to contribute more, but also for all energy sources to contribute more. And really, as Canada themselves, as a country, we have a target of reaching a net zero grid by the year 2035. So quite a lofty goal, and really substantial. It's really important that we have these substantial baseload assets that can help decarbonize our grids. Next slide, please. But the challenge, the challenge that the task force was looking at is how can nuclear do more? So what we know that nuclear contributes to a clean grid, but what more can we do on the nuclear side? What can we do behind the meter? How can we use steam and excess energy to really get the most out of our nuclear assets? And really that gets bucketed into kind of three opportunities. And low temperature electrochemical, obviously using electrolyzer technology potentially behind the grid. So if there are advantages that we can explore to really, instead of delivering megawatts to the grid, can we direct dedicated megawatts to an electrolyzer technology and enable clean production or green production of hydrogen that way? And obviously those technologies have a very high TRL level and really ready to go at this point. High temperature steam electrolyzers, we've looked at really leveraging those processes and using the steam available from our nuclear assets, and looking at what can we do with excess steam and any sort of nuclear maneuvering that can be done to really enable that process to take place. And that'll be kind of explored further by the production processes group as they really explore some of those specific opportunities related to high temperature steam. And then at a bit of a lower TRL level, the thermochemical processes, when we look at kind of the Gen 4 nuclear program internationally, and some of the SMRs and MMR opportunities, can we pair some of those nuclear technologies or dedicate them to specific hydrogen production opportunities, is also something we're kind of exploring within this entire framework of the hydrogen strategy for Canada. So really an exciting opportunity. And the kind of key question that we're looking to answer is really whether it makes sense to do what we call couple or co-locate hydrogen production with nuclear assets. So coupling being that you kind of pair the hydrogen production plant with the nuclear asset itself. So maybe not within, so that would be outside kind of the nuclear boundary, and exploring what that looks like, or co-locating being right within the nuclear boundary fence and having that right on site. What advantages do we get from that? And that's all pieces that we're looking at through this hydrogen strategy framework within these kind of three buckets of technology opportunities. Next slide, please. And really, the first step has been kind of creating an inventory of what opportunities we have as a country presently. And again, this hydrogen strategy framework, with that mix of industry, NGO, academics, and governments all at the table, provides us a really good opportunity to get that sense of what's out there. And as the lead for the Production Opportunities Task Force, it's been really exciting to see all these opportunities come in and see what individual industry partners are looking at, what they're exploring, and what they may be ready to do. And really what we've done is compile that all into an exhaustive list of opportunities that we are now looking at, kind of shortlisting which of those opportunities have the most significant or most are more likely to succeed and compete in this hydrogen economy. What are the opportunities that have the most likelihood of success, and really advancing those so that other task force groups can look at some of those unique challenges around economics or regulatory challenges or specific technology challenges as well. It's been really refreshing to see all this come together, and what we've done as a task force is bucket these opportunities into near, medium, and long-term opportunities. So near-term opportunities being those that could be producing hydrogen before the year 2030, medium-term being those that could be producing hydrogen before 2035, and with the longer term looking at kind of 2040 outward. And obviously there's kind of some inherent characteristics that come with both of those. Those near-term opportunities tend to be focused right on existing assets that we have here in Canada, whereas longer term get a little bit more theoretical to potential future assets that could be coming online. And it's really been exciting to get that work off the ground, and we're really well underway with that, and we'll be delivering kind of our short list of opportunities to other task force groups in the coming weeks, which is quite exciting, and there will be a lot of good discussion amongst those groups as we move forward. Next slide, please. And then, so that's kind of at its highest level at our federal government with the hydrogen strategy for Canada. But we also have provincial governments that are moving on this as well. And specifically, the government of Ontario here in the province has advanced just this year their low carbon hydrogen strategy, which kind of again takes that policy framework overview, but advances specific key actions that need to be undertaken to enable a hydrogen economy within the province. And what's really nice about the Ontario hydrogen strategy is it actually complements the federal strategy quite well and advances those specific opportunities, which is really great for us to see here in the province. And obviously working closely with Bruce Power, it was really nice to see one of the 8 specific actions that were outlined in that strategy were to assess the feasibility of hydrogen opportunities right at the Bruce Power site. So looking at how we leverage the Bruce Power nuclear generating station to create a hydrogen economy and create really a hub here in the Bruce Grey Huron region, and what we can do to make that work at the Bruce Power site and leverage the opportunities that we have from that critical asset. So it's really exciting to see the province move forward. Other pieces in the strategy is not nuclear specific, but definitely relies critically on both nuclear's contribution to the grid and exploring how nuclear can do more in enabling hydrogen production here in the province of Ontario. So it's a really exciting time. Next slide, please. And then it's not just governments that are moving on these priorities and creating a hydrogen economy. There's really a lot of interest from private sector. We have electrolyzer manufacturers here in Canada, here in Ontario, and here right in the Bruce Grey Huron region. And we have companies like Bruce Power really looking at this and acting on what the federal government or the provincial government has said, and they're excited to move forward and advance this feasibility work to see what can be done. The really exciting thing about the feasibility work that's underway at Bruce Power is the framework within which they're operating has a number of partners that will kind of advance a really specific feasibility work, which is quite exciting. So the framework that they've created to advance the feasibility work includes an electrolyzer manufacturer company called Hydrogen Optimized. So looking at how they can use that expertise within this feasibility work, but also they have Greenfield Global involved in that work as well, and Hensel District Co-op, which is an agricultural co-op, potentially exploring the off-taking the hydrogen that is produced at the site and using that within an agricultural context, which is really quite exciting. I think that's something that's been missing from other feasibility work across the country, is ensuring that there's an end user in mind or directly involved in that feasibility work, and that's really exciting to see advance. With that, again, I mentioned I would keep it light and keep it brief, and I'm happy to take any questions that may be from the audience, Eric, or that you may have for me. But all that to say, we really have a lot of good momentum here in Canada and here in Ontario, and really advancing some of these foundational policy frameworks and systems that will enable a really robust hydrogen economy as we move forward, and making sure that we're doing this in a thoughtful and deliberate way.
Fantastic, Chad. Very inspiring. And so I think what we do have time for a couple questions. And Ontario's always been an unusual place from a decarbonization perspective because it's already sort of finished the electricity decarbonization part of that activity. And but it's great that you're now kind of moving to, you know, how you can leverage that essentially to decarbonize other aspects of the provincial economy and so forth. So I assume that this kind of integrated collaborative work that where you're having industry and policymakers and so forth working on these strategies, you're sort of balancing both impact for decarbonization and, you know, sort of ease of going to market, right? You want to kind of make a fairly easy pathway to get the first bits of this sort of new hydrogen economy working, but then you also have to be focused on the, you know, achieving decarbonization as well. And so I'm wondering kind of how you've been sort of, how's that been going? Like how's that sort of balance and that tug of war been working?
Yeah, absolutely. It's a good question, Eric, and you're absolutely right. Ontario has been in an interesting spot since 2014, since we successfully phased out coal-fired electricity generation here in the province, and really it's been all about doing exactly that, leveraging the clean energy advantage that we have here in the province, and ensuring that can be a foundational piece for advancing these low carbon technologies. And it really does help other industries compete, as we kind of not necessarily take the entire decarbonization challenge out of the question, but we have a relatively small lift left to go. So we can actually use what we have now to advance these new opportunities with some certainty that we have that really, really good starting point. And it's quite helpful. And honestly, the input from industry across the board, the excitement from industry to be involved in this policy creation is really, really inspiring and really great to see. So having their input kind of at that ground floor has been really great, and ensuring some policy certainty as they make these key investments as they move forward, that kind of understanding that we built this together, it provides that level of policy certainty that they need to go to market.
Fantastic. Well, I think with that, I'll wrap it up. Thanks very much, Chad. And thank you to all the speakers. This was a very inspiring group of presentations. I think we've seen both kind of the scope of what's possible here in terms of manufacturing synthetic fuels. We've seen extensive sort of coordination and impact on policy. I think we're seeing really innovative collaborative models like the Nuclear Hydrogen Initiative and like the work that Chad's doing, which and the work that the IEA is doing as well. So I think we're starting to see some real kind of coalescing of the people that are going to make these things happen, and the policymakers who need to create the frameworks and so forth. So this was very, very exciting. And I would like to just say that please feel free to follow up with any of the organizations that presented here. The presentation and this recorded webinar will be posted on the Nice Future Initiative website, so you'll be able to look up all of that stuff. And in particular, Alina wanted me to mention that nuclear-hydrogen.org is the Nuclear Hydrogen Initiative's website, and they strongly encourage anyone who's interested to contact them and look into participating with them in the work that they're doing. So I think with that, we're ready to wrap up here. Great presentations, and we still have a lot of work to do, but this is really a kind of an additional pathway to achieving deep decarbonization that, as we can see, could be really scalable. And I think the Nice Future Initiative was really founded to find ways to accelerate the development of clean energy systems through an integration of clean energy technologies, including renewables and nuclear. And I think we've seen today that there's ways to extend this beyond the electricity sector, but into chemicals and fuels, and that should give us all lots to think about and lots to work on. So with that, thanks very much for joining. And please, one last thing, that the Clean Energy Ministerial is meeting in Pittsburgh between September 21st and September 23rd. And if you are interested, you should consider attending, and we will be there as well. Thanks very much, and goodbye.